Hi, team. I think I'll just get started and start recording also. So let me know you hear me, no problem.
Yeah, I can hear you.
Let's start it. Today we have hopefully you can get it done faster than this morning. This morning. So today we have chapter 2. We have 1, 2, 3, 4 topic. Let me switch my share my camera so you can see what I'm talking about. Box. So this is the full topic I'm going to cover today. It's from chapter 2. So first topic will be the gain and the loss. We're talking about communication. A lot of time we talk about the signal strength. Make it bigger, and during transmission, the signal will have loss. So loss in the media, and then we have to make up all the losses. That's amplifiers. And how do we measure those gain and loss? Most common we use decibels instead of ratio. When we talk about ratio, for example, 50% loss, 10%, those are called ratios, not commonly used in the industry. Instead, we use the decibel. Talk about the gain or loss. So if 50% loss, what is decibel? We said negative 3 dB. That's the same thing. That means the same thing, but we prefer the decibel for a reason. We don't prefer decibel to just show off. Yeah, that's one reason. Just show off. Of course, there's a better reason. Decibel is much easier a lot of time to do the math. The second topic will be second, third, and fourth. We all related. So when we talk about communication, we actually talk about analyze or control the signal in frequency domain. So the signals, we care more about the frequency of the signal instead of any other things. The signal can have many properties. Out of all the property, when we analyze communication, we have a huge interest on the frequency. So we will spend 3 sections about frequency. More importantly, this is the foundation of that analysis. That is called the Fourier transform. It basically converts any signal from time into frequency. So most common, we know our signal as a signal of vary with time. But that's not what interested when we study analog communication system. We insist more on the frequency. So let's get started with number 1. Number 1 will be the gain and the loss. Generally, that is how we calculate the gain. So if the output is much bigger than input, in this case 25,000 times bigger, that is called a gain. Okay. So gain is generally referred to the output divided by input. And another example, the second example, again, what do we talk about gain? The output is 6 watts. This can be an audio system, like your speaker. The input is only 80 milliwatts. The input power, the input is 75 milli. The output power is 6, the input is 75 milli. What is the gain? Gain is 80. So that's 80. So we can actually design the circuit very easily. When I was a student, I actually built a couple of those audio amplifiers because we like music. Everybody like music, and we want to play it loud in the dorm. And I built a couple of those, and we don't have money, so why we build our amplifier ourselves. It's very easy to build because the linear ICs, the power linear ICs make everything so easy. You just add a couple of external components, you have an amplifier. So this is the gain. Gain is created by amplifiers. So amplifiers. We can calculate the power gain or voltage gain. Both are in ratio. And it turned out we interested more in another way to measure the gain. That's called decibel. So what is exactly decibel? Well, this table basically tells you the relationship between the ratio and the decibel. So if the output is 50%, that's called negative 3 dB. That's right there. So the output is half. What about the output is 1/10? It's a negative 10 dB. What about the output is 10 times bigger, 10 times stronger? That's 10 dB. So instead of using ratios, we use the decibels in this case, it's power. So what is the definition of decibel? dB, the definition is 10. So this is the definition of this new quantities we measure. It's called it's not linear, it's exponential. It's exponential. So if this guy is what we're familiar. If this guy is 1,000, what is decibel? So if you plug in 1,000 here, 10 log 1,000. What is log 1,000? That equals 10 multiplied 3, which is equals 30. So that's right here. 1,000 is 30. Ratio of 1,000. Decibel is 30. Ratio of 10,000. Decibel is 40. Ratio is 100,000. Decibel is 50. I'm sorry, not 80. So let's look at the other directions. How about ratio is 2? Ratio is 2. Decibel is positive 3. Positive 3. So right here, 2 positive 3. So I want you to remember this table, at least a couple, not everything on this table, but a couple. So 0.5 ratio, power ratio, dB, 0.5 negative 3, 0.1 negative 10, 0, not 0, 1, 0. So if the ratio is 1, that means no change of the size. 1 is 0. 2, 3. 10, 10. 100, 20. 1,000, 30. So that's the decimal table. Probably nice to remember because, like I said, it is more widely used. People like negative 3 dB, then 50%. People like double. If you double your power, you don't say double, you say positive 3 dB, positive 3 decibel. Positive 3, that's double. Why are we doing that? Well, I already told you, make us sound more knowledgeable. One way to explain that. Well, there's another reason. For example, your input signal is 0 dBm or 3 dBm, we should say dBm. If that's your input signal, and then the gain is a 3 dB, another amplifier 10 dB, another 5 dB. That's all the gain. That's all the gain. What is output? Output will be 3 plus 3 plus 10 plus 5. Output will be 21 dBm. So now we find this really helps. Otherwise, you are doing multiplications. So basically, the decibels change multiplication into addition. Otherwise, if you have amplifiers in sequence, you multiply. For example, this gain is 2. This gain is 10. This gain is 6, for example. And the input signal is 1 milli. What is output? Without the decibel, you have to say 1 milliwatts multiply 2 multiply 10 multiply 6. That's what you do without the decibel. That's the ratio. So with ratio, if you have multiple amplifiers, you have to multiply. That's the ratio. With decibel, you convert all the multipliers into additions. Add. Every amplifier is another add. So the gain is just add all the decibels together is the gain. The reason is quite obvious. Log A multiply B equal to log A multiply log B, right? Anybody know this equation, right? Your math professor probably already told you from. So this exponential function will convert the multiplications of A and B into additions of A and B, the results, log. So because this math foundation, so engineers, we are built on top of math. So when you are in the field, you want to get the final output. You don't want to multiply, you want to add, right? Add is much better to do it without a calculator. So that's the reason why we prefer, instead of ratio, gain, or loss. This is a gain. This is loss. So when the gain is larger than 1 or equal to 1, we call gain. When it's smaller than 1 in ratio format, we call it loss. We found out all the loss are negatives. So negative dB means loss. Positive means gain. So that's another thing. Yeah, negative, we subtract. So if this filter, for example, is negative 3 dB, this guy is negative 3 dB, positive 10, positive 5, negative 3 dB. So all we do is subtract here. Instead of addition on the second device. So we started with 3 dB, negative 3, positive 10, positive 5. The result will be positive 15. So that will be the output, dBm. So that's the power of my output. If we have 3 devices started with negative, positive, positive. So I go through this really quick, but it's because it's simple. It sounds like exponential, decibel, but the main reason is make it simple. That means additions and subtractions instead of multiplications and divisions. Divisions, yeah. All right, the gain is provided by amplifier. Where are the loss came from? Yeah, where are the loss came from in a communication system? Many different ways. a typical system, majority of the loss came from the media. For example, I'm receiving television stations from Kansas City. Why the signals from Kansas City is so weak? Because it has to travel 60 miles, right? 60 miles. When you are sending email to your friends, for example, in which country you are from Philippines, right? Jimmy? Yeah, when you talk to your family members in Philippines, everything you typed is transmitted through a fiber. So that fiber travels thousands of miles. After reach the destination, it's really weak. That's where the loss, because long distance travel. There's another source for loss is called the skin effect. Skin effect. That's another quite common way our system is get lost, energy lost. Skin effect. But typically, if you think about a conductor, for example, wire gauges. If you wire up to ordinary outlet, you use small gauge wires, right? When you wire it to an oven or a heater or dryers, you use big wires. Why the big wire? Because the big wire has more area, cross-section area. That's more important. But unfortunately, that is not true for RF. What is RF? Radio frequencies. That's the radio signals. Unfortunately for RF signals, almost all the RF signals travels at the surface of the conductor, not inside, only in the surface area. That's physics again. That's pure physics. So when you are sending RF signals through a copper, it turned out it doesn't matter the copper is a pipe or solid copper. So that's why, because the skin effect is all about all the RF signal travel on the surface area. So skin effect. That effect can create a lot of loss if you're not careful. So that's another loss source, skin effect. The electrons only travel in the skin, not inside, even though you have a solid piece of copper. Solid copper still doesn't help. How about surface area? That's why we actually coated the surface with gold or silver. So a lot of time you see your conductor is coated with silver. Why silver? Because silver is a better conductor. Then silver is the best conductor, probably. So you coat it with a silver or gold. Why we coat it with gold? Because you have you're rich, right? Cover with gold. Actually, gold is stabilize your conductor because gold is extremely stable. So in some tough environment, when you coat your conductor, not because it looks better, right? For engineers, we do all things not because it's looking good, because its performance is good. That's our goal. So when we coat something with gold, that means we want to stabilize that conductor in some tough environment with humidity, with chemicals, with oil, whatever things can cause damage to the conductor. Once you coat it with gold, gold will be gold forever, right? Never deteriorated. All right, that is our first topic. Let's move on to the second one. Started on the second topic. we are talking about the frequency domain. So here's my piece of paper. Can't find it. So yeah. So now start with the second topic, all the way to the very end of this chapter. 3 sections. We all talk about the frequency domain. So we are interested in what does our signal looks like in frequency domain, and how we control it through a device we call filters. So once we know what our signal looks like in frequency domain, then we can add extra components or remove some of the components from our signal. We can control our signal in frequency domain. Now the first thing is, how does our signal look like in frequency domain? Let me do a demo. That is all the work by a French, I guess it's French. I didn't do the research, but sounds French, right? This guy is a mathematician. He basically found out how to translate from time to frequency. So this is called the Fourier transform. Fourier transform is a standard computer algorithm, so it's widely available. When I was a student, we actually write Fourier transform many different times. But now people just use it just like a standard module. Let me show you Fourier transform. On my I have a computer which do the Fourier transform. They call spectrum analyzer. So spectrum analyzer is a computer, dedicated computer, which analyze spectrum. When you analyze spectrum, that means you're looking at the signals in frequency domain. So let's see a spectrum analyzer. So everybody see the signal. This is a sine. I can change the frequency of the sine. This is a 2000 hertz, 3000 hertz, 4000 hertz. Let's move back to 2000 hertz. So everybody familiar with this signal, 2000 hertz. So it started here, half milliseconds, another half millisecond. So that's called the time domain. Notice up there is a little button that's FFT. It's called the Fourier transform, FFT. So once I hit that button, I will do a FFT. This computer will do the FFT. And let me stop at 50K. So now I will see my signal in frequency domain. This is the 10,000 hertz. I'm input the 10,000 hertz signal right here. That's 10,000 hertz. You see, 10,000 hertz. That's my signal. So this is 10,000 hertz, and this is the FFT of 10,000 hertz. FFT. How about 10,000 hertz of this? That's 10,000 hertz. Let's do FFT. That's what does it look like in frequency domain. Whoa, we found out it's 10,000 hertz, 20,000 hertz, 30,000 hertz, So the signal, a square, is much more complicated when we look at the time frequency domain, because you have this, this, and this. Let me turn off the green. So we just have one channel. So how about another one? Oh, this is called sawtooth. Sawtooth. What does it look like in frequency? Wow. 10,000, 20,000, 30,000, 40,000. It has a lot of components. So in time domain, it looks like this. That's time, that's frequency. Let's move to another one. All right, this one is so we found the sine. This is sine. Only one signal, only one 10,000 sine, 10,000 kilohertz. So what is the conclusion we got from this demo? The conclusion is sine has only one frequency. Sine has only one frequency. A 10,000 sine, just one frequency. A 10,000 hertz square, that's a square, has 1, 2, 3, let's keep it going. 50. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We also have the small on 20, on 40, on 60, on 80s. We have a bigger ones on. So we found sine, only one frequency. The square have multiple frequencies. What do we call those multiple frequencies? We call it harmonics. So a square has, this is called first order harmonic, second order harmonic, third order harmonic, fourth order, fifth order, sixth order, seventh order. Let's change to a sawtooth. A sawtooth. First order, right? First order, second order, third, fourth, fifth, sixth, seventh, eighth, ninth. So sine, no high order harmonic. Square has unlimited number of harmonics. So does many other signals like sawtooth. sawtooth, also has a limited number of harmonics. And this is the work of Fourier. He found that out many years ago, Fourier. So if you look at the signal, you can look at it either at time domain or alternatively look at frequency domain. So you look at the signals in frequencies. For example, human voice. Human. What if you look at the human voice in time domain? It's kind of like this, right? Human voice. But what if we look at this in frequency domain? We found out human voice generally are between 300 to maybe 3000 hertz. So that is there's up and downs. So there are components above 3000. There are components under 300. But the majority of our human voice, when we talk, is between that range. And that is important because once we figure that out, we can design a telephone system with only transmit this signal, right? That's exactly what your cell phone does. So when you talk to your friend over using cell phones, they are not transmitting anything above or below. Why? Because transmitting those are more expensive. Right now, you are paying maybe 1 cent, 2 cents, I don't know, or unlimited. Well, anyway, you pay. But if you want to, for example, do 6000 hertz, what happens? The voice is better. So your friend will, your voice will be more like in the same room. But you will pay more money because you will transmit, the information will be doubled. The bandwidth will be doubled. When you double the bandwidth you want to communicate, you need a bigger pipe. When you are using a bigger pipe, you have to pay for the bigger pipe, right? Nobody gave you for free. So that is that is why we interested in analyze our signals in frequency domain, because that's all ended up with a payload. Yeah, the bandwidth of signal you want to communicate is the actual payload. So this is your payload, you double the payload. So it's like a half-ton truck, carry half-ton, now your payload is 1 ton, you have to buy a bigger truck. And this is the same thing. The signal bandwidth determined is the payload, and you want to communicate, send it out to the other side, and you need bigger pipes if your payload is bigger. So let's go to the tuned circuit. When you are communicate, for example, 89.3, your payload will be 200 kilohertz. So that's megahertz. That's an FM station. So it started with 89.2, ended with 89.4. And this will be your payload. And look at that. That payload is much bigger than the 3000 hertz, right? When your human voice only needs 3000, well, this is 200,000. That means it's a 10-ton truck. It's a much bigger truck, heavy duty. So that is why FM broadcast is for music, because when you listen to music, you need to carry wider bandwidth. So what is the music? 20 hertz to 20,000 hertz. So that's music. That's human voice, 300 to 3,000. That's voice payload. So when you want to just transmit voice, that's the payload. But when you want to transmit a high fidelity, high definition music, the payload is 20K hertz. 20K hertz. Why do you need 200K for a 20K hertz? Why do you need that much bandwidth to carry this payload? Obviously, that's old technology. That's old technology. Just like the old television. Remember we have old TV, right? Now all of a sudden, every TV channel can carry 4 or 5 digital channels. Why? Because the old television system is not efficient. Same for the FM. The FM is the only limited analog system we're still using. I'm assuming, I don't know, maybe future we will change it to digital. Because the wider base of analog FM, we don't change, that's the only thing we kept so far, analog. Very inefficient. If you look at that, that's your payload, that's your bandwidth. This is like you are driving a 10-ton truck carry only 1 ton payload, right? 10%. And that's a huge waste of your payload. Loading capacity. That's old technology. That is why the cell phones, this is a 2G cell phone using the same technology. 2G cell phone or 1G, 2G cell phone use the same technology. So it's extremely inefficient using of your bandwidth. That's why the cell phone system to 3G, 4G, 5G, 100G, I don't know, Gs, right? So we invented new technologies trying to use this bandwidth more efficiently, so we don't waste our bandwidth. Bandwidth is the most valuable, one of the most valuable resources we have. That's our bandwidth. So when we listen to music or watching TVs, we are talking about a tuned circuit. What exactly is a tuned circuit? A tuned circuit is something like this. So suppose I'm listening to 89.3. So that's 89.3. I'm not listening to 89.5 or 89.1. So that's like your neighbors, your next door neighbor in frequency domain. So my station is 89.3. The next door neighbor is 89.1, 89.5, 7, 9, and keep going. Same thing for the other directions. So you have neighbors on both sides, but I'm just interested in this particular station. So how do you just listen to one station instead of every station? On the circuit. So tuned circuit, we're interested in a couple of things. First, bandwidth of tuned circuit equal to F2 subtract F1. So bandwidth, that's your bandwidth. Another we're interested in is the center frequency. What is the center frequency? That's the center frequency. It's not perfectly centered. Actually, it's so that's a second. Third, we're interested in the quality. The definition of quality, we not FC, I use FR rather than FR. So these three equations summarize everything you want to know about a tuned circuit. A tuned circuit, we're interested in the bandwidth. We're interested in the center or resonance frequency, which is somewhere in the middle. We're interested in the quality. Look at what quality means. These are kind of easy to understand. This is a narrow or wide, bandwidth, narrow or wide. This is kind of in the center, resonance frequency. What is the quality? Quality means selective. How selective your tuner are. So let's look at a couple of filters with different quality. So this is the high quality, medium quality, and the low quality. So when you are listening to your FM radio, which one do you prefer? High, medium, or low? I would prefer the high quality, assuming in between is 200. So this is 200K. So assuming everything, I cover my lot. I cover my station. So 200K from here to here, 200K. So I will prefer a high quality filter. What is the problem with this low quality filter? You hear 3 stations at the same time. Not only you hear your own station you want to listen to, you hear your neighbors. Maybe you want to eavesdrop. Yeah. No, that's not it. Because so that's extremely annoying when you can hear all 3 stations on your speaker talking the same time. So when we design a filter in this tuner, we want high Q. High quality. High quality means high selectivity. Highly selective. So I will only select 1 station out of 100. Or if I'm watching TV, I'm watching channel 3 or channel 2, right? Shenzhou, we have channel 2. We have channel 26. It's all represent to, it's now, we call it channel 2 or channel 3. Actually, it's all in frequency domain. So this is channel 2, channel 3, channel 4, channel 5. So channel 2 may be 50 megahertz. Channel 3 may be 54 megahertz. They are separated, television stations are separated much wider. FM station, the separation is 0.2 megahertz. So you have 89.3. Your neighbor is 89.5. But for television, your neighbor is you are at 50 megahertz. Your neighbor is 54 megahertz. It's 4 megahertz apart. It's like you have a bigger yard, right? Why you need a bigger yard? Because the television has more bandwidth. The TV signal has more bandwidth. You need that bigger pipe. So this is a much bigger pipe than the FM pipe. FM is a 0.2 million hertz pipe. This is a 4 megahertz pipe. 4 megahertz pipe for television. So now we know the tuners, and we want high quality. How we build one. So next topic is how we can build these high quality filters. So we only listen to our own station. When I was in high school, I actually built a radio with no tuner. Have you built a radio with no tuner? Anybody? A radio receiver with no tuner. So basically you receive every station. And when you listen to it for 10 minutes, you begin losing your mind. You begin run crazy. So that's how one way to get crazy is listen to that station, listen to all the stations without the tuner. You just 20, 30 stations at the same time on your speaker. Anyway, let's move on. How can we build a good filter? How can we build a good filter? I will go through this really fast because these material are considered so important and so old. Nobody cares. So important, so old, and the new technology solved it completely solved. So the filters are very complicated in the old days. Today, have you opened up your car audio system? Have looked at what's inside? Anybody repair a modern radio? When I was a student, I repair a lot of the old radios. The old radios are built the old way. How do you build the old radio the old way? That's how you build it. You have this. So these are called filters. In this particular one, is called a frequency notch filter. That's another filters. So inductors, capacitors, and resistors. This particular one is called the low pass. There's 3 different low pass. What's the difference? What's the difference?
Dr. Zhang,
yes.
To interrupt you. Are we going to need to know any of these, like the low pass filter, high pass, all that stuff? You said it's really not.
Well, I would say this is a communication class. This is not a circuit class. So I would hope the circuit instructor already taught you this.
All right.
It is 312, 212. What did you cover? 312, 212.
Well, I mean, you said that these are pretty much obsolete. Like this has all been.
Yeah. Because if you ever repair a modern radio, it's all digital. It's like switched. We'll talk a little bit about that.
Okay.
Yes, it's obsolete. So those are the obsolete technology. Why it's big? It's big. Have you repaired old radio? It's big. These are the inductors, copper, made of copper. Capacitors, they are all big. Physically, it's that big. Like a peanut butter. Each one is the size of a peanut, right? Like a peanut. So every component very big. How many you need? How many of those you need? In a typical radio, you need 5 of those. 5 of those. 5 or 6. So it takes a lot of space. Actually, many years ago, I think last year when Dr. Zhu is teaching this class, I think Dr. Zhu is still teaching the lab. He probably will ask you guys build an old radio made of this, and the circuit board is the size of 12 inches. But if you look at the modern radio, inside tiny components. So that's the old radio. Those are called passive. Yes, not required. I just look at it. Yeah, they are kind of just understand what they do. They are these guys are called band pass filters. Band pass. Why band pass? Because this guy is band pass. This guy is band pass. You have 3 combined. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2. 1, 2. This is 2. 1, 2. 1, 2. 1, 2. So this is 2. This is 3. This is 3. This is 2. This is 2. Why we have multiple? Because 1 cannot get the job done. This is 1. And then this is 2. This is 3. This is 4. This is 5. And finally, we are listening to our own stations instead of many stations. So you have multiple combined, increase the Q quality, make it a higher quality. Single one, the quality may be 12. You have 2 combined, you double the quality, maybe you can get the quality 15. And then you have another one 17, another one 21, another one 25. So keep adding, so your quality will keep going, keep going up, keep going up. With amplifier added, this type of filter are called active. Active filters are better because it has a gain. It can not only filter, it also make it stronger. So this is a passive. The output is actually weaker. So your input, the output is only a third of your input. It's weak. With this amplifier, the output can be 10 times bigger. Not only you filter it, also you make it stronger. That's exactly what we wanted. The signals you received from antenna have 20 stations or 100 stations, but it's really weak. So when you are building your radio, not only you want to selective, you also want to amplify. So you do it together. You do it select, amplify, select, amplify, select, amplify. That's how we do it. Select, amplify. And finally, it's strong enough, selective enough, and you can send it out to your speaker, right? Well, because this filter is so important in our communication system, the engineers spend millions of engineers, spend billions of dollars, develop new and better high quality. One of those most commonly used is called crystal. Crystal is made of quartz crystal. So this is a crystal, what it looks like, represent crystal. So if you have a computer, Raspberry Pi, let me grab a Raspberry Pi. I don't have Raspberry Pi anyway. If you look at any computer, you will find a quartz crystal. Quartz crystal. It's basically a piece of sand, silicon oxide. I think quartz means silicon oxide. By cut the silicon oxide crystal in different angles, different size, we can create a filter at different frequencies. For example, if you look at your Raspberry Pi, probably you will see a 20 megahertz crystal. Why 20 megahertz? Because the 20 megahertz crystal is the size of a small connector like this, small size. If it's lower frequency, means bigger size. So if you build a crystal of 2 megahertz, it's bigger than 20 megahertz. So 20 megahertz is the perfect size. So a lot of computers use 20 megahertz crystal, 20 megahertz. But your Raspberry Pi runs at gigahertz. 20 megahertz crystal will create a 20 megahertz clock. You do a multiply by 100, not 100, yeah, 100. You get 2 gigahertz. Now this is how you do it. This is called frequency multiplier. Frequency multiplier. We started with 20 megahertz, very stable frequency, and you do a multiply by 100, you got, and then this goes to your CPU in your Raspberry Pi. When you have this 2 gigahertz Raspberry Pi, well, actually the Raspberry Pi is 1.6 gigahertz. It's not 2 gigahertz, 1.6 gigahertz, or 1.4 gigahertz, depend on which one you buy. So not only these crystals can be used as oscillators, the crystal is also an excellent bandpass filter. So if we use this crystal as bandpass filter, what is the quality? We say the quality of a typical LC filter is 20. The quality equal to 20, Q equal to 20. Q equal to F. That's a typical quality of a classic or old or obsolete. We can use whatever word. So this type of filter, the quality is 20. How about a 20 megahertz crystal? What is the quality of a 20 megahertz crystal? Q equals 2. Any idea? Give me a number. Bigger than 20? How many zeros? One more zero? Yes, couple zeros. So the quality of this filter is extremely high. That's why it's very commonly used in communication equipment. You have quartz crystal as filter. Because this quartz crystal has extremely high quality. This is the highest quality, probably the highest we ever get. The engineers ever built. That's the highest. There's also other high quality filters. That's another example. When I was a student, we have a couple of more, but those are all obsolete. So we only introduced two. This is called SAW filters, surface acoustic wave filters. SAW filters are another alternative of high quality filters. This is how it works. The way it works, many of these type of filters work similarly. Electrical inputs converted to mechanical vibrations. This is thousands of hertz, or tens of thousands, or hundreds of thousands of hertz mechanical vibrations. And it turned out this ceramic base is very selective by the size and the strength of this ceramic material. The physical dimension of this ceramic material determines which frequency I can actually pass through. So opposite side is the receiver. So this is the transmitting. So energy, electrical to mechanical, mechanical back to electrical. So the output is input electrical, output is electrical, electrical in, electrical out. This is the filter. This is the filter. So only certain frequencies pass through. All the others are rejected because this mechanical device, this mechanical ceramic device, by how we cut it, what is the dimension, the chemical composition, the hardness of this ceramic material, it's all determined the frequency, which frequency can pass through. So this is a symbol for the ceramic filter. This is called ceramic filters. So we have a ceramic, we have quartz crystal. These are two types of filters. What about the latest? So if you have a modern radio, chances are this is what we are using inside your radio. That's the latest. Latest is called SCF. SCF, switched capacitor filters. What it means is this is a old type of filter, classic filter, and this is a SCF. This part. And by looking at the schematics, you think, well, this is much better, right? This is so complicated. So this is complicated. This is simple and easy. Resistor, capacitor, amplifier. In this case, capacitor, capacitor, transistor, transistor, a computer. So in this case, you have a computer. What are we missing here? This guy. So that's the whole point. We actually build a very complicated system just to substitute the resistor. So if I draw everything inside this block, if I draw right here, everything inside replace a single resistor. You may say, are you crazy, right? Yeah. Using so much to replace a single resistor. But it turned out this is better. This is called SCF. Why this is better? Because this component takes nanometers, tiny. So although this is hugely complicated, but for IC manufacturers, this second method is tiny. The first method, the capacitor is big. Resistor also big. How big? Instead of nanometers, this guy we are talking about centimeters. What's the difference between centimeter and nanometer? 10 to the power 7 times bigger. Go from here to here. So this guy is 10 to the power of 7 times bigger than this guy. So which one do you like? This or this? So the modern receivers are much smaller because the reason behind this we will skip. But this is just the magic of switch technology. The switches alternatively turn this capacitor on. And then if you take my circuit analyze class, we have DC analysis, we have AC analysis, right? Then we have switched. Did you remember what I say about switched? It's magic. It's not magic, but it sounds like magic a lot of times. This switched analysis, AC is complicated, DC is easy, AC is complicated, switched is magic. So that's one example of switched technology, change our communication equipment. The resistance equal to this equation, right there. Right there, that's resistance. So T is the period of switch. T is period. So by varying the T can be changed, right, by computer. So computer can change T very easily. This guy can be changed very easily. By changing the T, you can change the resistance. By changing the resistance, we can change the performance of this filter. Another switched application, another magic. How many switch? 1, 2, 3, 4. We take turns. 1 turn down, 2 turn down, 3 turn down, 4 turn on, and repeat. So we turn on switch number 1, and then we turn on switch number 2, then we turn on switch number 3, then we turn on the 4. After 4 is turned off, we repeat. So this is another switched technology. The input and output is here, input and output. Why are we doing this? Well, we're doing this to build two filters. Filter number 1, we call a what is a COM filter? This is what a COM filter is. It is selective, repeatedly selective. So if this is 10,000, 20,000, 30,000, 40,000, so this is a COM filter. COM filter is this. Yes. That's what the computer is. Frequency, gain. This is the computer. So the frequency and the gain. 1, 2, 3, 4, 5, 6, 7, keep going. So that's what this switch technology accomplished. This thing can also be a tuner. Why it can be a tuner? It's an excellent tuner if we just look at this part or this part. That's a tuner. Each is actually a tuner. So this can be station 1, station 2, station 3, 4, 5, 6, 7, 8, right? It's your stations. It's your station. So by picking one component, we can tune to every stations we wanted to listen to. So we can build a tuner. So that is probably how your modern receiver are built. That's the technology. So this is the latest. This is 30 years ago. 30 years ago. 30 years ago. This is 80 years ago, right? 80 years ago. So 80 years technology, 80 years old. This is not 80 years. This op amp is some new. But 80 years ago, we don't have op amp. We just have a amplifier based on transistor. So just more complicated here 80 years ago, but everything else is the same. And 30 years technology. And the newest. Switched. That's the keyword, switched. This technology use a switch to get the job done. The last topic is a Fourier transform. It's a pure math. We already covered this. This is what it looks like in time domain. And this is what it looks like in frequency domain. So a square in frequency domain, you have first order, second order, third order, fourth order, fifth order, sixth order, forever. This is the math. We just skip that math because math is too simple. We're not concentrate on the simple stuff. We concentrate on the more complicated stuff, right? Math is too simple. So this is called triangle. We don't show the triangle, but triangle, same thing. First order, second order, third order, fourth order, fifth order. This is a square. Oh, this is square. Okay. Square have first order, third order. Sawtooth has first order, second, third order. If you remember, that is exactly what I show you at the beginning, right? A square, you have this. A sawtooth, let me show you again. So just remember this. Square, time, frequency domain. Sawtooth, time, frequency domain. And let's end with a repeat of the same demo. I will do in a repeat, same demo. Okay, that's so if I input is psi, oh my, I actually disconnected one wire. So this is your sine. Right now it's 10,000 hertz. 10,000 hertz. This is your 10,000 hertz sine. And let's do a FFT. Remember the FFT of sine? A square, right? Let's see. Uh-oh. What is that? Oh, this is a sine. So sine has only one component. That's right here, right here. Let's do a square. So that's a square. So you have 10,000, right? You have no 20,000. You see, 10,000, 30,000, 50,000. For square, you do not have 20,000 component. You only have 10, 30, 50. How about I change to, now I have 10, 20, 30, 40, 50, 60. That is exactly what we showed on the theoretical. Here. So a square, we have 10, 30, 40, 50, 70, the green. A sawtooth, we have 10, we have 20, 30, 40, 50, 60. We have every harmonic. Well, this is something about FFT. Right now, this FFT is not high quality, right? You see, 10, but it's not very sharp, very sharp. So how can we make it sharp? Make it sharp by taking more samples. Okay. Now this is my sine. This is my sine. I have so many sine. By having many sines, when I do FFT, this will look like 10,000, 20,000, 30,000. This is a sine. This is not sine. This is sawtooth. Sawtooth. What if I change to square? Right now it's square. 10,000, 30,000, 50,000. What happens here? 20,000. In theory, we should not have 20,000. That's the theory, right? But we live in a real world. In real world, not only we have 20,000, a small, little 20, we have little 40. Look at here. What is this guy? A little 45, right? A little 45. What does that mean? Anybody give me an idea what that means? Real world, not perfect, imperfect world. Imperfect, imperfect. This is not a perfect square. Not perfect square, right? This is not perfect. Yeah, it's not perfect. If you look at it, it's not a perfect square. So that's what's the difference between the theory and the real world. In real world, nothing is perfect. So if you look at it in FFT, you don't see a perfect series. In theory, we only have this guy, this guy, this guy, this guy. In reality, not only we have a small 20 hertz, notice we also have a small 0 hertz. Small 0 hertz. What does it mean, 0 hertz? 0 hertz means a little bit of DC power. How strong is this DC power? Negative 50 dB. What does it mean, negative 50 dB? This guy is negative 20 dB, negative 20. This guy is negative 50 dB. What does that translate in the strength in ratio format? What does that translate in ratio format? Negative 20 dB is 1,000 times stronger than negative 50 dB. It's a 30 dB difference. The difference between negative 20 and negative 50 is 30 dB. The difference between negative 20 and negative 50. What is the 30 dB difference? Right here. 30 dB means 1,000 times weaker. So that means for every 1 watt of square power, there's a milliwatt of DC power on my power supply. There's a milliwatts of DC. So it's not perfectly half and half. My square is not perfectly half and half. That's a perfect half and half. That means this and this is perfectly equal. The positive and negative are perfectly equal. But that never happens. Sometimes this is bigger, sometimes this is bigger. They are not perfectly equal. There's a 0.1% difference. That 0.1% difference will show up here as this little guy right here. This little guy right here, which is 30 dB behind the 10,000 hertz, the main power. This is 1,000th of the 10,000 hertz. It's a DC signal. So that's all I want to have for today. This chapter 2. It's a big switching from timing time domain into frequency domain. So in communication, we looking our signals in frequency domain. That is what we are looking right now. After FFT, we look at our signal in frequency domain. So anybody want to comment, questions before we dismiss? I guess everybody fall asleep. I'm not sure. All right. I will turn.
I think we're awake.
Yeah.
Oh my! Everybody's
Yeah,
awake.
we're good.
Wake up! Yeah.
Yeah,
Yeah.
don't worry, sir.
That's a
Everybody's
good
awake.
nap. That's a good nap. I
My favorite time of the day is when your class is on, so I can take my daily nap.